Up to now, we have talked a lot about dynamic optimization problems. We started with non-stochastic problems or deterministic problems, then moved on to stochastic problems, and now we are moving on to as well stochastic problems, but potentially of a more complex nature. If you want to read on reinforcement learning, I can highly recommend to read the Sutton and Bartow book, Reinforcement Learning, in the 2nd edition. It's published online for free, so you can download the book and either print it yourself or just read it on screen, or you can purchase the book in online or in a bookstore. You can also find lecture slides and videos of David Silver, former student of Sutton, I think, on the address that you can see down there. So if you want to look deeper into some of the content that you see in the subsequent weeks, then you can also look into these videos. Now, consider yourself in a situation that let's start with why do we need reinforcement learning techniques? We have already seen solution techniques for stochastic dynamic optimization problems that were kind of complicated or kind of had a long time horizon. So why do we need reinforcement learning, or why do we need other techniques at all? And the question, there's 3 points or 3 ideas why we might need different techniques. So consider yourself in a situation where you do not only have a single state, so for example the capital stock of a country or an economy, but you have many different states. And we've already seen it takes some time to only optimize over 2 states. We did that last year. And it already took a very long time for the algorithms that we've seen to converge so that we ended up with the correct value function. That was only for 2 states, but consider yourself in a case where you have many different states. You can have 5, 6, 8, 20 different states, then all the methods that we have seen so far will fail to end up with a suitable value function in finite time or in feasible time. So it will take years and centuries to compute to only obtain the value function. So in these cases, you cannot really use the dynamic programming approach that we used last year. The second scenario might be that you don't know either enough or anything about the transition equation itself, or you cannot directly write down, or you cannot directly compute the expectation, because the transition equation is so complex, or the transition process is so complex that either computing the expectation of the future states is either impossible or again not feasible in a finite amount of time. And the third scenario is very closely related to the second scenario, is that we only observe the world by data, so piecewise, time by time, and we don't, at the beginning, we don't know anything about the transition equation or about the process that is behind the transition, but we are learning everything piece by piece by observing data, by observing the real world and observing what is happening. And in all 3 cases, you'd be pretty struck with the methods we treated so far. And if it's only due to lack of time, which is of course one important reason when tackling a little more complex problems. Before we start with working with reinforcement methods, I'd like to introduce the notation that is used through the reinforcement learning literature, and that's also used in the Sutton and Bartow textbook. It's a bit different from what we have seen before, but some of the notation is the same, some notation changes, and some concepts change slightly. Usually, we work with states as we worked before. We denote the states by S, and we denote the current state with S and the state of as of tomorrow or the next state with S prime. What we have called a control before is now called an action, small a, and we denote this by small a, and sometimes we also need the actions as of tomorrow, then we would denote these with a prime as well. In reinforcement learning, we are interested in learning a policy, so a decision-making rule, and that does not necessarily need to be the optimal policy, so the optimal choice or the optimal action at each state, but it can differ from the optimal policy, which is the only policy we have accounted so far in dynamic programming, where we always maximized something and always derived the exact optimal policy. So pi is any policy, any decision-making rule, and later on we see that these are very close to the optimal policies because we still want to maximize somehow some, for example, discounted cash flows or something, or discounted rewards or utilities. Then pi of A given S is just the probability of taking some action A in a state S under the stochastic policy pi. So for example, if one action A star is the optimal action, then pi of A star given the state we are in should be rather high, so 99.9% or something. The value function now is not...
Sorry, may I ask something?
Sure.
So the pi expression, the policy, right?
Yeah.
Is a mapping between actions and states. Is that correct? So this is a function that tells me what to do given any state. And the pi also denotes a probability, or is it the same?
It's the same. So pi is just a policy, and the policy is described as a probability of taking an action in a state. So given we are in a state, this function returns a probability. So these two are the same object.
Before we didn't have that, right? So before we knew when we are in some state, I don't know, whatever the state might be, then we already didn't know what to do, exactly what to do.
Right.
Yeah,
before and
the probability distribution, isn't it? That's a probability distribution where we put 100% on one action.
Right, exactly.
But another question here is, so do we have to assume that the set of actions is finite?
For now and for the rest of the term we will. It's not completely necessary to have that, but it's more complicated to derive the method or to use the methodology. So for the whole rest of this term, we are going to have a finite action set, yes.
But in principle, this pi of A given S could also be a conditional density function.
Yeah.
Mm-hmm.
Okay, what we called the value function before has been under the constraint, or under the has been what we received after optimizing. So it has been always according to the optimal policy. This changes here as well, because right now we only have the value function according to, we can have value functions according to any policy. So for example, we can have the value function according to the policy of randomly choosing any action. Then we would get, of course, not the optimal value function, the value function that is with respect to the optimal policy, and we denote the optimal value function, so the object that we previously called the value function, with v star, and with v pi we denote the value function with respect to any possible or any current policy pi. And we can also split up the value function, or look into the value function in a little more detail by looking at the action value function, which is nothing else than the value function of taking an action A in a state S, and after that behaving according to the policy pi. So in state S we decide to do action A, and after we did this a single time, all the subsequent periods will be evaluated according to policy pi. That's often very, it's a useful construct to derive the policy, because if I have a finite set of actions here, I can go over all potential actions in the state, determine which is the optimal action regarding my state, and then derive the policy directly from the action value function. This is a very neat and useful construct here to evaluate actions. As I said, for now we work with finite state and...
Sorry to interrupt again.
Yeah.
The question concerning this Q function, is that related to what we call the continuation value? Because in a way it splits up the current value, because currently we are doing any action A, which need not be part of the policy pi. And then after that, we behave according to pi, and that's the, in a way, the continuation value then, isn't it?
Yeah, the continuation value was not with optimizing over the current decision, was it?
The continuation value is, well, in the Bellman equation, of course, it is for the optimal value function.
Yeah, then
But
it's then the continuation value that we defined before is Q star of S and A star. That's the continuation value, and this is a more general construct here because we can put in any action and any policy.
Okay.
All right, for now, we, despite having finite action sets, we also assume a finite state set. So we have countable states. We will loosen this assumption in the second half of the reinforcement learning, where we approximate the value function. But for now, for today, and for the next weeks, I think 1 or 2 weeks, we will use only finite state spaces and thus compute exact value functions. As I said, as we denoted before, S and A are the action, ST and AT are then the actions at time t. Each action leads to 2 things. First, a reward, so something we get in return of our action. So utility, a cash flow, or whatever is the reward of a current action. That's typical due to ST-1 and AT-1. So we get a return in the period due to what we did before in the period before. That's a bit different to the notation that we had before, where we received the return in the current period. With GT, we denote then the total following the total return following some point in time t. So the discounted sum of rewards. From this point in time, we add up all these rewards, we discount them, and we get an object that tells us how our value function looks like in a certain state.
So the sum runs over k, not over I, isn't it?
Oh, sorry, yes, the sum runs over I. Sorry, yeah. The sum runs here over I, if I put an I in here. Yeah, correct, thanks. And what we denoted by the transmission equation before is in here, in the reinforcement learning context, denoted by the probability of a future state and a reward being in a current state and obtaining and choosing some action. So I am in a state, I choose an action, and the probability distribution or the probability of transitioning from this state and this action to a new state and getting a reward is what is our transition equation in here. So the law of motion in the dynamic reprogramming context is translated in this transition probabilities here. And then you can read that also in the Sutton book. The value function is denoted as the expectation under our policy pi of GT given we are in some state or given our starting state. That is, given our state, we of course behave according to the policy pi, and according to policy pi we transition to new states, get new rewards, choose new actions, and then transition to new states again, get new rewards, and so on. And the expectation of the sum of all the states up until termination, capital T, or until infinity, if we have a task that doesn't end, is then the definition of the value function. And we can just plug in this in there. So we can see this is here now for the infinite case horizon, just the discounted sum of the future rewards given we start at a certain state. And then we can do the same thing as we did in the Bellman case. We can split this into tomorrow's reward plus the discounted future g, so the g that starts in t plus 1. And then we can expand this whole expectation operator here first by looking at all the possible actions according to our policy. So because this expectation is taken over the finite action set, we have the sum of the probability of choosing an action given we are in a state. And then we have in the inside the probability of transitioning from our current state using the action that we have chosen here to a new state with a certain reward. And we have to multiply this by the reward we get plus the discounted value function of our new state. That's basically very similar to what we did before, but in the new notation of reinforcement learning.
May I say something to the equation? So I think at least in my perception, there are 2 points that are worth stressing. Mm-hmm. Also compared to what we did before. So first of all, I mean, this is called the value function, right? But this has nothing to do with the value function we had before because there's no optimization here involved. So this is basically a recursive notation of what is going on if you do something.
Yep.
Basically, as far as I understand it. So this is one important thing, and the other important thing is that the notion of controlling the system is somewhat different in a sense, because here we are talking about, which is a clever way, I think, to work with real work problems, but it's a bit different to what we did before. So what you pick here is basically this stochastic rule, right? Which comes, I mean, from the perspective of an economist, this comes a little bit strange because you would never want to. Well, it depends. When you are a game theorist, this is okay, but in general, you want to pick just one action, right? What you basically do here is you pick this probability space of actions, right? It's like a mixed strategy, somewhat.
It might be a mixed strategy. It might also be this probability here might also just fall down to be 1 for a certain value of A and be 0 for all the other values. So that is what we are going to learn.
Yeah, true.
So what the algorithms I'm presenting or we are presenting in the subsequent weeks are going to do, that this probability here collapses or is closely to collapsing to 1 for a single action and to 0 for the other actions. But in principle, it could be anything.
Yeah, that's a good point. Thank you.
I have a quick question.
Yeah, sure.
So in line 2 of the equations below, it says RT plus 1, and then we have GT plus 1. Why shouldn't it be GT? Because then we have RT plus 1 2 times, 1 times discounted, 1 times not. Or am I missing something?
The question is good because the notation is a bit different than before, because GT up here starts with RT plus 1.
Mm-hmm.
So GT plus 1 here starts with RT plus 2.
Okay.
Because we have the shift from T to T plus 1 here. We have the shift then from T plus 1 to T plus 2. So we don't see our T plus 1 twice in here, but just a single time.
Okay. Thank you.
Okay, in principle, we want to know either V pi or V star. Sometimes we're interested in V star, or not sometimes, but usually we are interested in V star, of course, because we want to have the optimal policy, but it's very hard to get the actual optimal policy using reinforcement learning methods. We'll see that today. So very often we need to stick to a policy pi that is close to the optimal policy, but not exactly the optimal policy. We call getting to know the value function the prediction problem. So we predict the value function. And with it, we want to know the optimal policy pi star, or any policy, the optimal policy pi star, or a policy that is close to the optimal policy. And we call this the control problem. Starting from scratch, so we don't know anything either, any of those two, as we did before. And in the course of the reinforcement learning part of this lecture, we will encounter different algorithms to learn V pi and pi. In all of these algorithms, and in all update routes that you see later on, the equal sign doesn't indicate an equation, but it's just an assignment of new values. So it's more like the equal sign that you see in code as compared to the equal sign in an equation. There might sometimes be actual equations, but whenever I talk about updating rules, or whenever you see code like an algorithmic structure on the slides, the equal sign is not an equation, but an update rule or an assignment of new values. So let's start with an algorithm that we have already seen, that is value iteration. And that is the algorithm we basically used at the end of last year, but now in a different notation, so in the algorithmic notation that you will encounter in this part of the lecture. The algorithm and the notation is taken from the Sutton book as well. It's, I think, on page 83, but that might be incorrect due to an old version of my book. So if it's not on 83, I'm sorry. What we did in last year was we initialized the value function arbitrarily, then went over the whole state space, and for each state we computed the value function using the recursiveness of the Bellman function. And we did that until the algorithm converged. And once the algorithm converged, once we obtained the correct value function, then we could derive the optimal policy from the value function. So that's basically what we did last year. And we can also write this down in the algorithmic notation of the reinforcement learning literature. So we first start with initializing the value function with arbitrary numbers from R. So for example, with 0 or with 1,000 or whatever. Sometimes it might be sensible to, again, put a bit more thought into initializing this value function, because if you initialize it rather close to what's the true value function, then of course everything goes much faster. We also initialize the policy. Sorry, let's just go back to the question Jörg had with the pi object and the pi as a probability. Now we see. Now I see what you meant. We can also denote pi as the action that given in a certain state. So it either is a probability, it can either be a probability, and then we denote it by pi of an action given a state, or pi can just return the action that is chosen in a certain state. Does it make sense?
Yeah, but then you are using two.
But then we are not using. Then we don't have a stochastic policy. So this might be. So this initializing here, I think, is incorrect, because we want to initialize pi of a given s. So we initialize the policy arbitrarily. So for example, with a 1 for any action given the state. In R, it's not important to normalize these probabilities. So just initialize any random policy. And then what we did was we repeatedly updated the value function. We started by saying that the difference between old and new value function was 0. Then we went over all possible states, took the old value function and stored it in this small v, computed the new value function as the expectation over all states, over all future states and rewards, with our transition equation and the future and the respective reward plus the discounted value function of our new state, and then we took the maximum over the action of these many actions that we could choose and stored this into the new value function, computed the difference between the old value function and the new value function, and once this difference got very small, then the algorithm converged and we had obtained the correct or the final value function. And from this value function we could then easily derive the optimal policy based on that we just take the maximizing action. So this is actually pi star here, not just pi. We took the maximizing action over our value function. These are basically the steps that we obtained last year and that we did last year to obtain the value function. So this would be the, so to say, reinforcement learning formulation of the algorithm that you have already seen and used. We won't use this algorithm because, as you can see here, this sum can get very cumbersomely large if the transition equation is more complex. If we have more states, then we would need to sum over all these potential future states, which might get a very, very large sum. Instead, so for this case, we needed to know the whole transition equation. So we either need to know a model, or we need to know a transition equation, we need to know how the world behaves, or we need to assume a transition equation, or we need to assume a law of motion. And for computational feasibility, we required that this transition probabilities are in closed form, because we don't want to simulate them, don't want to compute them in a way that takes much time, but we require these to be available in closed form so we can compute them rather quickly. So this is, of course, a rather restrictive assumption, because very often we don't know a transition model because we only observe the world as it evolves. And because of that, very often we either don't have this probability at hand, or we don't have it in closed form, or we can only simulate the world, or we can only simulate the transition equation, or we can only simulate what's happening in the world. So these are the two reasons why we are not using the algorithm I just showed you, but why we need to learn about other algorithms that help us navigate around the problems. The first idea would be, instead of assuming that we know the transition equation and that we know the transition model exactly, we loosen this assumption by saying, okay, we don't require knowledge about the environment, or don't require complete knowledge of the environment, but it is enough for us to simulate how the environment evolves. So we only need to be able to draw the next step of our environment. So we only need to simulate a future state, and we only need to simulate a reward based on where we currently are and what action we obtain.
May I interrupt here?
Yeah.
I normally understand knowledge about a distribution as either knowing the exact formula of the density or anything, but also one way of knowing a distribution is having an algorithm that simulates from that distribution, because once we have an algorithm, we actually have to know everything about that distribution. So in this case here, I would say we do require complete knowledge if we want to simulate the environment. Of course, if we just observe it step by step, we don't.
Right.
But if we assume we are able to simulate, then we have to know the law of motion.
That's true that we know the law of motion in the way that we can simulate from the law of motion, but assume you had to compute this probability by simulation each and every time in each of these steps here over each future state, over each future reward. Then this task here, this maximization, or this computing this expectation here is infeasible in a realistic time, a realistic time frame.
That's a matter of how to compute the expectation in the Bellman equation. That's the argument here is that it's computationally infeasible,
yeah.
Or at least cumbersome. But your argument was that the reinforcement learning approach is better because you don't need to know the complete distribution.
Yep.
But if you assume that you can simulate the law of motion, then you do have to know the complete distribution.
Sure, if I want to simulate it, I have to know. And in most cases, the example we are using are more of an illustrative nature, in which we can simulate the transition equation. But reinforcement also works if we cannot simulate it, if we can only observe the transition equation. So we can either simulate here because it's easier for us and more convenient for us to do so, but it would also be enough to just observe the environment, to just observe what's happening. So we not necessarily need to be able to simulate it. Observing the environment and observing the transition will also be sufficient.
So the assumption that we are able to simulate is just to, well, kind of simulate that we are observing the environment.
Yeah.
And assuming that we don't simulate.
Yeah.
Okay.
All right. Monte Carlo methods require episodic games. And an episode consists of several iterations of the transition equation. So we play several time steps. Each of these iterations has, of course, a state, an action that we choose, and a reward that we receive. Until the episode terminates, and once upon termination, we update our value function based on what has realized in the game, and a new episode starts. You can think of these episodal games as, for example, a game of blackjack where you draw cards until you either win the game or lose the game. While drawing cards, you don't really learn much about the value function, but after the game has finished and after you have seen whether you lost or won the game, then you can, of course, update your value function and update everything you know about what to do with which cards at hand exactly. Another example might be driving a car around a corner. If you assume that you want to have a self-driven car and you want to teach that car how to drive around a corner, you could just start the car, let the car, at the first iteration, use just a random policy, look what's happening, and after either a certain periods of time or after the task of going around that corner is completed, you look at the car, you look at the time it took to go around the corner, you can look at the speeds it was at, you can look at potential damages of the car and so on, and then you can update the value function based on what you see after the car has finished its job. And I think the example of driving a car around a corner is a very good example where you need to actually do both. First, you simulate the whole process hundreds of millions of times probably to get an idea of how you can drive a car around a corner. And once you did that, you can take your engineers, build up a real car, fit what you've learned about the way to go around a corner into the real car, and then let the real car drive around the corner and see if what you derived from simulation fits the real world. And another example might be to invest in futures. You buy a future for something, then you hold that for a certain period of time until termination of the contract, and then you either see that that it was a good decision to buy this future, or whether it was a bad decision to buy the future if prices didn't behave as you expected them to. In all these examples, we only learn
Sorry.
yeah.
May I ask something?
Sure.
So what's the difference to what we did before with those examples? Weren't we able to do this before as well?
You were able to play blackjack, I say yes. You were able to say something about the futures, maybe also. Driving the car around a corner would be a task that is pretty much infeasible with the methods we've learned before. Because driving a car around a corner contains so many states: the speed, the direction the car is going at, potential damages, other people on the road, pedestrians, and so on, many sensors in the car. So many states that need to be taken into account at the same time that you cannot solve this problem in feasible time with dynamic programming. And that is only if you know the transition equation. If you have an actual car driving around an actual corner and you only receive sensor readings in real time, then you only receive data in real time, then you couldn't use the dynamic programming approach at all.
Mm-hmm. Okay, thank you.
Yep.
So it's really just a feasibility issue. And I think you're completely right that in principle, it would be able to solve these problems by by dynamic programming if we know the law of motion. But in having a solution in principle is not really helpful.
Yep.
if it's not feasible to do it in practice.
Yep, and even if I only observe data, I could use the dynamic programming as well, because with the data I observe, I could somewhat approximate or estimate a transition equation. So it is also possible to use dynamic programming, I think, with data, but as I said, it's not feasible in real time, and it's not feasible in real world applications. So in other applications, in real world applications or in more realistic scenarios, we would need different methods. A little more terminology before we actually see the algorithm that is behind Monte Carlo methods. I already said that that the aim is to obtain a policy that is the optimal policy, or at least very close to the optimal policy. Because, of course, we want to know how we can drive around the corner the best way, how we can play blackjack the best way, or how we can invest in futures the best way. And we don't want to have a random way of driving around a corner. And we don't want to randomly draw cards until we lose or win the game. So we call an action a greedy action. That's just the action that maximizes the value function of a certain state. So what we denoted before we can denote this by A star. And a greedy policy is a policy that only contains greedy actions, which is not necessarily the optimal policy, because we might not necessarily have learned the value function. This here is V of S. It's not V pi of S. It's not necessarily the current value the correct value function according to a policy, but this is just some value function. So a greedy policy does not necessarily need to be the optimal policy if the value function hasn't converged yet. In the end, when the value function has converged, and when we obtained the correct value function, then the greedy policy coincides with the optimal policy. If we now deviate a little bit from the greedy policy, we call this policy type an epsilon soft policy. It's a policy that selects the greedy action with probability 1 minus epsilon, but deviates with a small probability epsilon from the greedy policy. So for example, epsilon is set to 5%, then in 5% of all cases we don't choose the greedy policy but choose any other policy. And one possible version of epsilon soft policies are the epsilon greedy policies, which we can denote by the probability of choosing action A given in the state S as 1 minus epsilon for the optimal action and epsilon divided by the size of the state space minus 1 for all the other actions. So the probability of deviation is split equally between all the other states. And as I said, A star is the maximum of the action value function, so the greedy action.
May I ask something to the first bullet point or concerning the first bullet point?
Yeah.
Because it still puzzles me a little bit, notation and vocabulary wise, so to say. So you said that the greedy action is an action that maximizes the value function,
yeah.
right? And the value function is describes something. What I mean, this is maybe in my ignorant view, I would call this just the present value, right, of the future, of future outcomes, somewhat. And you said that we do not necessarily need to consider some optimal action plan or something. But I mean, to calculate what will happen in the future, you have to assume what you would do in the future, right? And what is that, what you assume what you would do in the future? Because the greedy action just refers to the contemporaneous action that you choose, right?
Yes, but so if you assume that this object V is a value function derived according to a policy that is close to an optimal policy, so somehow an epsilon greedy policy after the algorithm has converged, then the action that maximizes the value function is of course not just the present, the instantaneous utility maximizing action, but the action that maximizes the value function.
Yeah, true. This contemporaneous does not refer to the reward, but to what you do. So contemporaneous means I have to choose something today, right? In any way. Yeah. I have to do something.
Yeah.
And let's call this the action, right? Yeah. And then you define the greedy action as the thing that I do today that maximizes the value function.
Yeah.
And my question is, what is this value function thing? The value function is obviously basically the present value of what will happen in the future, given that I do in the future something. And what is this doing something in the future? You have to assume something about that, right? But what is it? Is it just, I would just pick anything, or is it? Do you know what I mean?
Let me just go a few slides back where we defined it. This one here is the value function of some state under some policy, V pi. So, and that's what we want to obtain in the end. In the end, we want to see the value function due to any, that is with regard to any policy. So with regard to any decision-making rule. So that we also know what we are going to do in the future, and to do tomorrow, what we know, we would know what we need to do the day after tomorrow once we arrive there, and so on.
Then the VS.
Pardon?
What is then the VS? I just thought that we are after the small V star of S, which is the optimal policy.
So this is the very same. I think I just mixed up notation here a bit. This is just V of S, so the small V of S.
But the V pi of S, or the? Because I mean, I have to what I conceptually do not get is how can I calculate the value function without saying anything about what I will do in the future?
I cannot. I of course cannot.
But-
And this v of s might be, for example, just the value function as I initialized it. So before learning the value, the correct value function, this is just, this might just be the object that I just initialized 5 minutes
So
ago.
you pick basically what you are saying is basically, okay, I just assume some action that I will choose in the future. I mean, this is what you do by initializing in a sense.
Yeah.
Okay,
And the greedy
okay,
action
right.
is just a definition that this action is the one that is the best given our current state of knowledge. Our current...
Given this initialization, I mean,
At any time. So one step after initialization, after I run an algorithm for 2 times, 2 iterations, I learned a bit.
yeah, true.
And then the greedy action again is the action that maximizes what I know then about the value function. As we had in the case of dynamic programming, before the value function converged, we also had to choose some actions. And we also had to evaluate what is happening tomorrow with our current states. And this was not optimal because it only got optimal at the time where the algorithm actually converged. Before it was only optimal to our current state of knowledge, but not optimal in total. And that's the same idea here. So the greedy action or the greedy policy. Now I'm alone. Are you back again? I think I was gone for a time. Can you hear me now again?
Yeah.
Yes.
All right. And the same holds for the greedy policy. The greedy policy is the optimal policy if I have learned the correct value function. Until then, it's just a greedy policy, a policy that optimizes, that chooses the action that currently maximizes what I know about the value function. Doesn't need to be the optimal action at all. And we'll see that the differences and why this might be problematic in a minute.
And just a small notational question, what you call capital Q, the function capital Q, that is then the equivalent to capital V of S.
Yep.
So some Q function which need not be optimal.
Yep.
But which is just happening along this iterative procedure.
Yep.
Mm-hmm.
So consider the following setting as an example. We can play 2 lotteries, whatever a lottery is, it doesn't matter. The first one pays according to a normal distribution with a mean of 3 and a variance of 1/9. And the second lottery pays according to a normal distribution with a mean of 9 and a variance of 1/9 as well. We initialize our value function with 0 for all state. And the state here is pretty simple, either 1 or 2, because the state is just an indicator of which lottery we play. There's no complicated law of motion because there's no complicated transition or something taking place here because the future state is just today's decision. So no really important law of motion here. We can just focus on what is happening in each of the states. So what optimal policy do we learn with MC methods? I said we need to play an episode, and after the episode, we reevaluate or we recalculate our value function with the new knowledge that we gained throughout this episode. We start the value function with 0 everywhere. So at the first iteration of the algorithm, we don't know anything about these 2 lotteries. So we need to choose between them, but how could we do that? Yeah, then just take one of these lotteries at random. So at the beginning, we don't have any idea what to do, so let's just start with playing the first lottery. We draw R1 from the normal distribution with mean 3 and variance 1/9, and that one will be larger than 0. Variance 1/9 is a standard deviation of 1/3, so we are 9 standard deviations away from 0, so this one will be a positive return. Then we update the value function at the state 1. We say this is, of course, R1, because we don't know anything else about the value function. So let's update it. V1 is equal to R1. V2, of course, remains unchanged at V2 equal to 0. And then we see V1 is larger than V2 because R1 is larger than 0. In all of the subsequent games, if we choose the optimal, if we use a greedy policy, we will choose the first lottery, obviously, because the value function of the first lottery is larger than 0. This one, the value function of the second state of the second lottery is 0. And so in all subsequent games, we will stick to the first lottery and we will obtain in each time a positive reward here. So we will get a very good estimate for the first lottery, for the value function of the first lottery, and we will never play the second lottery, which is of course problematic. So given our current knowledge, this is optimal. So the current knowledge is we know something about V1, but we don't know anything about V2. Or V2 is equal to 0. So let's play with the second lottery, at the first iteration. Then of course R1, the reward of period 1 will be drawn from a normal distribution with expectation 9 instead of 3 now. So this one is also of course larger than 0. We update then V2 is equal to the first reward. V1 in this case remains unchanged at 0, and V2 is larger than V1. And in all subsequent periods, in all subsequent games or episodes, we will choose the second lottery. And again, given our current knowledge of the world, this is optimal. So in both cases, we end up with something that seems to be optimal because we of course don't know this in this case. Now, given we had complete knowledge about the world and about the behavior of these two lotteries, the left version is of course not optimal because we're choosing the lottery that gives a lower reward than in the right case. So given we had complete knowledge, the behavior on the right-hand side, always choosing the second lottery, is optimal. So whether or not we'll ever find the optimal solution in this game only depends on our first decision, if we play a greedy strategy every time. If we did that with an epsilon greedy policy instead, we choose any lottery at random at the start, of course. Then we draw our first reward, we update V of k. At the next decision with probability 1 minus epsilon, we choose lottery k because V of k is larger than 0, as in the example before. And with probability epsilon, we choose the other lottery. So with a small probability, but larger than 0 probability, we will learn something about the other lottery as well. So we are exploring the state space. We are exploring all the relevant states. And after some iterations, we will have explored both lotteries, so both states, and could then exploit the best lottery. And that's the trade-off that we will always encounter in reinforcement learning. We need to somehow explore the state space. We need to get to know what is around us in the world, for example, when we're driving a car around a corner. Or we need to know economic variables that impact our state or our rewards. And we can do so by obtaining actions that are off the optimal action, or at least of the greedy action, because we don't know yet whether this greedy action is the optimal action as well. And once we have encountered much of the state space, or at least sufficiently enough of the state space, then we can exploit this, the setup, the problem, by then turning down the epsilon value to a smaller value. So we are making exemptions from the greedy state and then optimal state much less frequent and gain much more reward. This epsilon determines how quickly we explore the state space, of course. With an epsilon of 50% in this toy example, we would, of course, every time choose at random which of the lotteries we play, and after 3-4 iterations, we would have learned everything about the state space. Of course, an epsilon of 50% is way too high for real-world applications or for more interesting applications with larger state spaces. So epsilons between 1 and 5% are usually a good way to start to explore the states. Now the problem here is we are not behaving optimal anymore. So we have the wrong action with a probability epsilon. Hence v of pi is not optimal, and pi is not the optimal policy, but just a policy rather close-ish to the optimal policy. We don't maximize anymore, so the maximizing operator, by choosing the optimal or the greedy action, is weakened a bit. So the question might arise, does this policy or does this value function still converge as we had in the dynamic programming and Bellman case, where we had the maximizing operator that ensured convergence? And the question is, does that still happen here? And the answer is yes, it does, because we can transfer every epsilon greedy policy in an equivalent greedy scenario. Rather simple. By looking at this case here, we have a lottery scenario as well. We maximize the expectation of all the future rewards. The rewards are normally distributed and so on. So just the same scenario we had before, but written down in a little more formal way. So what we maximize is the expectation of the future rewards by choosing the future state. So the transition equation in the epsilon greedy policy is obviously the future state is our current action. So if we choose 2 today, then tomorrow we will play lottery 2. We will get a reward according to the normal distribution with expectation 9. And then we can choose again for the day after tomorrow and so on. The policy on the other side is we play action A with probability 1 minus epsilon. And we play action 3 minus A star. So if A star is 1, then we play action 2. If A star is 2, we play action 1 with the remaining probability epsilon. Now let's translate this to a greedy scenario and the maximizing, a completely maximizing scenario. Then we would just say that the transition equation is the state tomorrow, based on our action, is either A star with probability 1 minus epsilon, or it's 3 minus A star with probability epsilon. In this case, this function is a function of A star. So we don't, this should be A star here, or this should be an A. So the transition equation now has some randomness in it, but our policy is to just choose A star every time. But it just doesn't happen because nature intervenes and somehow disturbs our decision in the transition equation or via the transition equation. But the policy here is to just maximize and to just use a greedy policy, and then thus we are still maximizing again, so we can always find a greedy representation with additional randomness in the transition equation to any epsilon greedy policy. And this is a very good scenario here, because then we are in the maximizing world again that we have seen in the last year, and then we can ensure that the algorithms I show you are eventually going to converge to the value function, or to the value function, but no longer to what we would call now the optimal value function.
And this is a very tricky way to see that it's just a reinterpretation, this greedy epsilon greedy policy approach, reinterpretation of what we already did before. And I think it's pretty obvious in this toy example, where we have next period state just equal to today's action. But does this hold in general as well? So if the transition equation is more complex and depends on the current state and some randomness and the current action,
then the action, then we could still split up the transition equation into a transition equation path that is based on our optimal action, and a transition equation path that is based on any other random action. So we can always write down an equivalent greedy scenario where we choose an optimal policy, but the transition is a little different. So we can always go from some transition equation to an equivalent transition equation changing between epsilon greedy policy and an equivalent greedy scenario. Yeah.
And you could also think about the objective being beforehand the expected future path, given some evolution of the state, to be a more complex thing when the control is a random variable as well. So you have a more complex expected value, but you still want to maximize that. And as long as you want to maximize all these sufficiency conditions hold, I guess. I think this is the deeper insight of this.
Yep. Okay, then let us spend 5 more minutes before you can have a little hands-on yourselves on the first algorithm that uses Monte Carlo methods. That is the on-policy first visit Monte Carlo control for estimating the policy pi. That is approximately pi star. So we are estimating a policy, or we're learning a policy that is close to the optimal policy, or that should be close to the optimal policy in the end. We initialize pi as an arbitrary epsilon soft policy. We will do that as an epsilon greedy policy. There will be an exercise in a minute, and I uploaded a template, and in that template pi is initialized as epsilon greedy. We initialize the action value function arbitrarily for all states and for all actions. We initialize a list of returns for all states and for all actions, and we will store all the returns of all state and action combinations that we encounter the first time in an episode. So if I encounter a state and choose an action once and do this a second time again, then we only look at the reward that we get after the first visit, hence the name first visit Monte Carlo. This list we will use to compute the actual value function, and we do this by first generating an episode. And in this toy example of learning lotteries, it's just choose a lottery according to your policy, compute the reward of that lottery, and then the episode is of course done, because the episode only contains of a single step. Then we store all these, so this is the episode, starts at state 0 with action 0, then the first reward, and in the lottery example, that's it. But of course, there can be more complicated scenarios where you have to where you then obtain a next state, and the next action is computed according to the policy, and the reward at the second day is obtained as well, and so on until termination, so until the episode ends. And then we can, once the episode ends, we update our value function. And we do that by initializing g. That was, if you recall this, the remaining value from a certain point in time, so the discounted sum of all the future rewards. And then we go back in time from the beginning to the end, compute the new g, so the discounted current g plus our reward that we get tomorrow. If the state and action combination has not occurred yet, so is not in S0A0, S1A1, and so on and so on. So if this combination hasn't happened before, we append g, so our value function estimate, to the returns that we have seen at state S and action T. So we take the list that we already have, put one single return after that, and go on. And then the action value function at this state and the current action is the mean of this list of returns that we have obtained. So in each episode we are looking at, we can add at most one element to this return list, but with more episodes running, of course, this returns list gets longer and longer, and then the mean here is the average, of course, of what we would expect choosing an action A in a state S. Now we have our action value function. We might have, after some iterations, have informative values in our state for all of the potential actions. And then, of course, we can derive pi A given I am in the state as epsilon greedy with respect to this Q function. So if I know Q for all of these actions, then I can always, of course, determine which is the best action or which is the greedy action, and the rest of these actions get a probability that is according to epsilon divided by the number of options minus 1. And we do this until convergence, either or until we have seen a large number of episodes. In the exercise that is coming in a minute, you'll do this for the lottery example with just 50 episodes. So you generate 50 times an episode of playing a lottery. And then do all these steps, so append the reward from that lottery to the returns list, compute the mean of the returns list, and then derive the optimal policy. So the intuition is we run the whole episode of our game, of our economy or whatever, of driving around a corner. Then we evaluate the full episode, so not just step by step, and after each step we learn, but we only learn after the whole episode has been played. And then we update the value function and the epsilon greedy policy according to the complete episode that has been taken place. All right, there is one exercise, the learning lotteries exercise, that's currently also the last exercise in the exercise book. So I think we have 20 minutes left, which should be sufficient to at least start the exercises and get a little hands-on to learning the lotteries yourself, unless there are any questions, of course.
Just one question concerning the slide number 17, I think. That's this one here. The loop, the for each loop, does it run backwards in time, or does it run? Why is that?
Because we want to compute
so we
G using the returns here. We could, of course, if we went forward in time, we would need to, in the first period, of course, add up all the discounted returns, and then in the second period, we need to subtract something from that. I think that might work as well. But I think it's a more elegant way to go backwards in time to discount G and just add the future return.
Yeah, I was just a bit puzzled. I think I overlooked the first line or the third line. So you start by generating the process from time 0 to the final time.
Yeah.
And then you evaluate this series running backwards.
Yeah, the first line of code here, or of pseudocode, is generating the episode, so playing the game. And this loop here, so this one happens in a loop, of course, as well, but there was no space to write it in loop notation. And this loop here is the update of the value function.
Because otherwise it's hard to find whether ST80 has already appeared if you run backwards in time and there's no time.
Yeah, true.
In back of you, in your back, or in front of you, depending on the direction you go, then that wouldn't be possible. But no, it's clear now. Yeah.
Okay, good. Any other questions? Okay, then I'm going to start the breakout sessions. Okay, welcome back, everybody. The time is already up. So we are going to start with this problem on Tuesday again. I hope the template was a little helpful, but I think the problem is so much simpler than the algorithm I just showed you that you won't need most of the algorithm. So we are going to start with this again on Tuesday, and I'll... Ich konnte dich auch hören, Mark. Okay. Yeah, we will start with this exercise on Tuesday. You will see that this is a little unsatisfactory because the result of this exercise is not exactly what you would like to see. And we will see solutions to the problems that occur subsequently in the next weeks. So enjoy the rest of the day, enjoy your weekend already, and see you on Tuesday. Bye.